next speaker is Andres Sevtsuk, and he's with Cityform Lab at MIT and one of the developers of the Urban Network Analysis Toolbox to deal with complex data, and I have to find it here, complex data and related to human activities in cities, and he'll be talking about redundant paths for urban network analysis. So I know it's here somewhere.
It's the PDF.
Oh, it's the PDF. Okay, that's why I don't know it. It's number 6. Okay, there we go. Good. Yep. So let's see. View. Full screen. Where is it? There it is. Right there. There we go. Yeah.
Thank you very much. Good afternoon, everybody. So I'm here to introduce a new edition of the Urban Network Analysis Toolbox we have been developing at the Cityform Lab, and this is work we've been doing together with a number of other people. Raul Calvo, who's here as well, Michael McConnell from MIT, and Reza Amin Darbari, who has been working with us in Singapore. Let's see if this works. Yeah, so let me start out by arguing that having redundancy in cities at many levels is fundamental to why cities function well, why people like to live in cities, etc. Cities offer not just one place to work, but many, not just one place to go to school or to buy goods from markets, but many. And one of those things is also travel in a city. Different people have different needs, and having the availability of different travel paths to get from A to B is, I think, quite fundamental to satisfying and making people happy about environments. And the availability of these paths is much dependent on urban form and environmental geometry. The way we design and build our built environments sets up the rules of the game of how you can actually get from place to place, or whether you can or cannot. And different urban environments, such as grids, for instance, offer naturally many ways from getting A to B. On grids, there's typically, between different city blocks, multiple routes that are exactly the same length. So if you imagine the Manhattan grid, you can get from Midtown to Lower Manhattan on literally hundreds of thousands of different routes without really having to extend the walk. So you can choose the walk or choose the route that satisfies some of the other needs that you want to maybe get done along the way, pick up things or visit friends or avoid some traffic. Well, other environments that I would refer to as semi-lattices are sort of a combination. In some places they offer many routes between A and B, in some places they're more constrained. And what's called sort of tree graphs in graph theory terms, which are very common subdivisions in suburban neighborhoods, typically just offer one and only one route between any origin and destination. So if you start from any building here and try to get to any other building, there's only one so-called simple route where you don't backtrack or repeat any nodes from getting from building to building. Now, much of the software and many of the tools that are available for analyzing urban environments along networks actually simplify the picture and assume that travel occurs only along the shortest path. The shortest path could be the least cost path, the least time path, the least distance path, but they're typically shortest paths. And so when we calculate typically accessibilities in urban environments, then we look at walks or travel from some origin point I to different destinations around it, and typically just follow the shortest path. And this is also true for the toolbox we've been building and distributing as open source in our lab called the Urban Network Analysis Toolbox. And many of the indices for accessibility, when we calculate along the networks how many grocery stores you can reach, or how much floor area, or how in between other traveling paths certain buildings are, we usually do it along shortest paths. This is one example of that. This is a neighborhood in Singapore, and we've calculated the betweenness index here. The betweenness index basically assumes that there's trips starting from certain points and ending up in other points along shortest paths, and then we weigh the analysis here. We compute betweenness from public transit stops, which are these black dots, to all the individual retailers in a particular neighborhood called boogies, and we keep track of where these flows would go, and we weigh the analysis by the actual observed ticket tap-outs at all the bus and subway stops. So these are sort of predicted pedestrian flows in and between buildings in that neighborhood. But again, this is along shortest paths. So what we've done recently is developed an additional part of the urban network analysis tools, which we call redundancy tools. Redundancy tools calculate 3 new indices that we launched this past fall. They calculate redundant paths, which basically indicate all possible paths from A to B up until a certain detour ratio above the shortest path, meaning that if the shortest path is x, then we're willing to deviate up until a certain level above x to get to the destination and find all the paths that are available in those constraints. The redundancy index, which I'll explain in a minute, basically is a ratio between the linear lengths or the weights found on the linear lengths of all redundant paths divided by the linear length of the shortest path. So it's a kind of a ratio of how much more you get if you take into account all the redundant paths compared to the shortest. And then we also have an index called the wayfinding index. So the redundant paths, basically the tool allows one to find all possible paths from A to B. This is a so-called HDB neighborhood in Singapore, in Punggol. It's essentially municipal housing, public housing district. And as you can see, this path is actually not very long. This is an MRT stop or metro stop, and this is an entrance of an apartment block. And just between these, because the walking network that was surveyed is so incredibly dense, there's over 467,000 paths for getting from A to B. And we can rank them in terms of how likely they're to be used or how often they're reused in this analysis, and then sample a certain set of paths that might be more different for further study. For instance, for studying the actual observed walking preferences of people. The wayfinding index is an index that relies on redundant paths, but what it computes is the likelihood of finding a destination B from an origin A by taking completely random choices at every intersection along the way. So it's kind of a tourist index. That's why I used the St. Mark's Square of Venice here. But in a way, it assumes that if you're totally blind and go from A to B and just turn random directions, then it computes the probability that you will hit B at the end within a certain detour constraint. And we think it can be used to study things like places in a city that are most easy to find from all origins, from all buildings to certain destinations, for locating facilities or public monuments and things of that kind. And finally, the redundancy index is that ratio between the sum of lengths of all redundant paths divided by the length of the shortest path. So if we allow the detour ratio to go, let's say, 5% above the shortest path, then these are the blue are those routes that are available beyond the shortest path for getting from A to B. And the index here says 2.86. That means that 2.87 times more linear network becomes available if we extend 5%. It goes up if we extend 10%, it would go further up, etc. But what's interesting about the redundancy index is that it can be computed very quickly using network analysis for many origins and many destinations at a time. So we can compute which locations seem to have the most redundancy available to them. The red locations here, the index goes above around 10, which means that something like 10 times more path length is available within a, in this case, 15% extension of the walk above the shortest. And it gets even more interesting if we start weighing the analysis. So it's one thing to say, okay, we have 5 times more linear network available, but obviously, we're not just interested in the linear network per se, we're interested in things that are on that network. So if we weigh the analysis by destinations that are on those networks, such as coffee shops, then the index tells us how many more coffee shops become available on a certain walk from A to B, or many origins to destination, if the walks can extend beyond shortest. So it can be weighted by any numeric attribute. It could be the number of parks or trees or coffee shops or stores, and the redundancy index would then tell us how many more of these amenities become available if we're not only analyzing things along the shortest path. And there's an example of these types of weights. So this is a walk from a shopping center, 4th floor of a shopping center in Singapore, down staircases and routes through certain buildings and streets down to a subway stop. And this is the exact same walk along a different route. And we basically can show that the weights are very different. We can choose routes as we do as pedestrians in cities, depending on what we want to pass by. And I would like to just conclude with showing very briefly 2 data sets we've also made available. So this toolbox is freely downloadable from our website and open source. We very much invite people to change it and write extra code to add things to it. But we've also recently surveyed in great detail a few neighborhoods in Singapore and provide the data sets on the website as well, which can be used as inputs for testing. This is in Bugis and this is in Punggol. They're roughly a square kilometer in size, and they document all the building footprints and structural walls, all the pedestrian routes inside and outside of buildings, and all the businesses that are in those environments. And here's a 3D snapshot of these data sets in Bugis. So you can see that a lot of the businesses go up several floors. There's around 4,000 businesses in this district, and these gray routes are all the walking routes that are actually available in the environment. So we're now using the data set to study pedestrian route choice and things like that. So thank you very much. The white paper is available from email or from our website.